Hello, everyone. The following is the third in a series of lectures covering Chapter 40. Today, we'll be talking about the Compton effect. One of the ways that the sort of classic wave model for light was challenged was by Arthur Compton around the 1800s, early 1900s, and his crew of lab mates when they were measuring the reflection or the scattering of X-rays being shot onto electrons. Now, you saw how during the photoelectric effect, light can be absorbed by electrons, but the EM radiation in general has different ways of interacting with particles depending on certain factors. So, for more energetic light, what can happen is that an electron might not absorb it, but rather there be some scattering. So, the same way that perhaps a laser bounces off a mirror, so will an X-ray shot into an electron. What classical physics would tell you is that, well, yeah, X-rays hit the electron, and part of the X-ray gets reflected off, but some energy kind of gets transferred over into the electron. So that means that the reflected X-ray loses energy. And if that's true, then being a classical wave, then we should expect the amplitude of the X-ray to decrease. But what they found that changed was the wavelengths. The wavelength of the X-ray seemed to increase, which is the same as saying the frequency. They're related. The frequency of an X-ray after scattering with the electron had decreased by a amount that was only proportional to the angle of scattering. They thought that the frequency that they would measure, had nothing to do at all, with the scattering, with the energy, but rather the frequency that we'll measure of the scattered X-ray will have more to do with just, the Compton shift, since the electron's moving on. Thus, there'd be like a bit of a Compton effect when you get the X-ray reflecting off the electron, and thus there'd be like a few measurements of the scattered frequency of the X-ray being different. But no, it turns out that for any particular angle, scattering angle, the shift in frequency was always the same. So to explain this, you could ditch the model of light being this wave that, like mechanical waves, its energy is tied to its amplitude, but rather its energy is tied to its frequency. And then, because of a lack of a sort of Compton effect happening when measuring the frequency of the observed X-rays, Compton then modeled the X-ray as a particle, and its energy was directly proportional to the frequency. So what this meant was that the sort of way to look at the X-ray hitting an electron and scattering was the same way you look at just two pool balls, one hitting the other, and both scattering off in opposite directions. So this was following a very classic particle matter interaction model of conservation of momentum. Thus, the X-ray and the electron, momentum and energy will be conserved between them. Thus, the X-ray hits the electron like a pool ball hitting the other, gets some energy into the electron. So the electron moves off one way, the X-ray bounces off the other way, and thus it has lost energy, which, being tied to the frequency, means that it's going to lose frequency and thus increase its wavelength. Remember that for radiation, the frequency and wavelength are always inversely proportional to each other. And much like in classical physics, you can actually determine, if one pool ball hits the other and you get their scattering angles, you can actually figure how much energy what the original pool ball lost. And that's actually related to the scattering angle. And thus, you can actually figure out by how much the wavelength increases after scattering using the Compton shift equation, which is essentially a function of the scattering angle theta for the X-ray. Note that the terms in front are basically constants because you have the Planck's constant here. H, you have the mass of the electron in the denominator and the speed of light as well. So given that this term is constant, it's usually called the Compton wavelength, which is just a bit less than a few nanometers. Normally, just plug this in as S rather than having to calculate HM over C every single time. And on the right, we see the lab results where effectively the most noticeable shifts in wavelengths happened when the scattering angle was increased. So that's what the function here tells you. Because of the cos theta, it means that as scattering angle increases, so does the shift, which means more energy is passed from the photon that makes up the X-rays to the electron. And here's just a drawing of Compton's lab setup. You have a way to produce X-rays through some probably radioactive material or some kind of light, and that's going to strike electrons that are bound to some metal target. And then with combining it with a crystal spectrometer and ionization chamber, you can get an idea of the X-rays wavelength after scattering. And with the right setup, you can make it so you're only collecting scattered X-rays at a certain angle. So you have an assurance of what the scattering angle is based on how you set up the spectrometer and the chamber. So this question is just asking if you're trying out different types of radiation to scatter off electrons, which of this will have the biggest fractional shift? So fractional shift just means, the total shift in wavelength over the original wavelength. And this is the total shift, right? This is the formula, Compton shift formula. But the formula only depends on the scattering angle and just a bunch of constants. So this doesn't depend on the wavelengths at all. So to calculate the fractional shift, you divide this by the original wavelength. So whichever wavelength is the smallest will give you the largest fractional shift then. And thus the smallest wavelength goes to X-rays. And that's our answer. Note that the scattering angle for the electron, phi in this case, not necessarily the same as the X-ray. Remember in classical physics, by conservation of momentum, different angles can be the same. That's okay, because as long as overall momentum is conserved, it's fine. Then here, just another textbook example, just showing you that you can find the answer. A lot of the time, the wavelengths are going to be really small, so be careful with units. And it's just asking now, okay, what if the scattering angle is bigger than 45 degrees? What happens to the wavelength? Well, because we have a 1 minus cos term here in the shift formula, the bigger the angle is from 45 to 90, cos is going to get smaller. So this term is going to go to 0, which is going to make the shift overall bigger. So if there's a bigger shift, that means that there's a bigger difference between the initial and final wavelength. That means that the final wavelength is a lot longer than initial, which means a lot of energy was lost. So you might recall from not last chapter, that was relativity, but a few chapters ago, we saw how when you shoot light through slits, they create a interference or a diffraction pattern, or even both. So that was because of the constructive and destructive interference that waves can do. And for Thomas Young and company, that was enough evidence to say, well, this is clearly proof that light behaves like any other wave, a wave on a string, a ripple in water, or sound itself. But then we saw the Compton scattering happen and the photoelectric effect where light was acting like a particle. So we need quantum mechanics to be able to describe light as having this wave behavior when it comes to things like diffraction and interference, as well as particle behavior when it comes to the interaction with electrons that lead to photoelectric effect and scattering. Classical physics cannot involve both wave and particle models, cannot be woven into a single thing, but quantum mechanics can. So we bring in the good physicist Louise de Broglie, who found a way to relate the um, classic particles to waves. So we had already seen that the energy of light was not related to the amplitude of the waves or anything. It was actually related to the frequency, and on top of that, as seen from the Compton effect, from the Compton scattering, was that between the X-ray and the electron, there was conservation of momentum. That meant that the X-rays, I mean, that the radiation, originally thought to be just a wave, must have some momentum. There must be some way to measure linear momentum, and thus the momentum of the particles is shown here, and that's related to the wavelength of the wave. So right away we had a relationship stating that light has this particle property momentum related to a wave property, and thus de Broglie thought, okay, well, if there's a bridge between light, being a wave to being a particle, there's a bridge between the momentum and the wavelength. What about electrons? What about protons? Is there a wave property that they have? Is there a wave nature to classical particles as well? So he argued then that it's not just light that can act like a particle, it's just that everything in nature can have wave and particle characteristics. At this point, 1923, where we've seen light acting as a particle sometimes, but we haven't really seen particles acting like a wave. But de Broglie, like any good theoretical physicist, postulated that and thus found a way to relate a particle's momentum to the wavelength of its wave nature. So every particle is really a particle and a wave. Thus, their momentum that we can measure is related to the wavelength of this wave representation that's also intrinsic to them. And thus was born the de Broglie wavelength formula, which you see here, that relates a particle's momentum, again, classical momentum, which has its mass times its speed, to the particle's wavelength. And likewise, he devised that just how a photon, its energy is related to the frequency of its wave representation, he thought that then a particle's energy is related to the frequency of its wave. So with this, he had a bridge where classic particles with measurements like momentum, like energy, could be related to wave properties like frequency and wavelength. Thus, to fully describe phenomena, we need to describe light and matter as both having particle and wave properties. In the day-to-day world, we really don't have to do that. This classical physics is enough to describe what we see in terms of kinematics, dynamics, and so on. But in the subatomic world, the behavior of particles and light can't be explained with classical physics. So we introduced the principle of complementarity, which is the axiom at which quantum mechanics behaves, which is simply the statement that wave and particle models, whether it's matter or radiation, must complement each other. So around 1926, de Broglie's theory was beginning to be vindicated, as it turned out that electrons could produce diffraction patterns. And this actually happened accidentally. Two physicists, Davidson and Germer, were basically shooting electrons through crystals. And normally, people have known by now that you can shoot light through crystals and you see a diffraction and interference pattern on the other side, because the spacing between the crystal's atom act as a grating. But it seemed like the same thing happened when you shot electrons through a crystal. If you set up an electronic detector on the other side, you'd see that an interference pattern was being produced from the electrons. And based on the interference pattern, using the same formulas for what you'd use in the interference pattern of light, like in the Thomas Young's double slit experiment, they were able to determine the wavelength matching that pattern. But that wavelength of the pattern came from electrons being shot into the crystal, so that wavelength was tied to the electrons. And it turns out that that measurement followed de Broglie's formula for the relationship between the wavelength and the momentum of electrons. And following that year, multiple studies would show that indeed electrons do form diffraction patterns, much like light does. Clearly, we can no longer talk about an electron and a proton as just a particle. We need to think of it as having this wave-particle duality. So before that, quick quiz. I have an electron and a proton. They have the same de Broglie wavelength. And the question is, which of the following quantities are also the same for the two particles? Well, if they have the same de Broglie wavelength, remember that that's proportional to 1 over the momentum. So the momentum for both should be the same then. The speed and kinetic energy, and by consequence the frequency, are not the same because it's true that yes, the two particles, electron and proton, have the same momentum, yes, but they have different masses. So the speed's going to be different, and thus the kinetic energy, and therefore the total energy as well, which means that the total energy being related to frequency, if the total energy is different for the electron and the proton, then so will the frequency. And here you can see that the Broglie wavelength for an electron is some tiny amount, less than a nanometer. And again, you're never going to be able to like zoom in on an electron and see, that you're never going to see like a wave of this size. We'll talk about what you actually observe when you look at an electron in later chapters. Now, interestingly enough, you can use mechanical formulas for, quantum mechanic formulas for real-world objects. So a rock has a corresponding de Broglie wavelength. The electron microscope is a really cool device that takes advantage of wave properties of electrons to image objects. So basically, electrons are technically better than light as imaging devices because when you observe something with a microscope or a telescope, your resolution is based on the wavelength of light. And electrons, as de Broglie stated, also have a wavelength to them. And electrons typically have a much shorter wavelength than visible light. So that means that if you can use electrons to view things, they will offer a better resolution than visible light. So electron microscopes basically use kind of like this electron detector that's passing over a microscopic surface, and it's able to tell you, where the electrons are, how far away from the detector, so you can get this image of this kind of like this height map essentially, because it tells you, okay, well, at this height there's this electron here and here. If you lower the plate a little bit closer, there's electrons here and here. So then you get this kind of 3D map through electrons that are reaching your detector. And another cool thing is that the reason why electrons are able to reach the detector is that in classical physics, you have your plate hovering over your microscopic surface, and everything in that surface, which is whatever you want to look at with your microscope, the electrons are usually bound to that surface. But due to the electrons' wave properties, an electron is actually able to tunnel into the little detector, and thus it can be scanned. So that's what lets you scan over tiny things with your electron microscope and see really small things, because now you can see things the size of an electron's wavelength, which is why you can then image like microscopic bacteria like this little guy. Anyways, one last section for now. We're going to introduce a new model to describe particles. Since we now established that, okay, well, electrons, protons all have wave properties as well, clearly the model of a particle in space isn't enough to fully describe them. So we're going to make do with a new model that does describe a particle as a superposition of waves. This model is called the quantum particle model, and it's very flexible, but overall, um, it's described through one or more than that, many waves superimposed on one another. And with it, believe it or not, despite the fact that it eventually just a bunch of waves stacked on top of each other to make up the model, this is a model that actually contains all the information we need to know to get the physical measurements of particles we are familiar with, like the speed and momentum or position or all that. So to start off with our quantum particle model, we'll begin with like just a single wave, and this is just the most basic perfect wave we can find, which is just one, like the one shown here, that just has one wavelength. It just exists everywhere on space. It's not bound by anything. So this is not like a wave on a string. This is just a wave that just it's being emitted through all of space. That's why it's ideal wave. It's not realistic, but it's the foundation of the model. So, what sets a particle apart and a wave apart? Many things, but one of them is, when you think about it, is the location. Think of a ripple of water in a pond. Where is the ripple? Can you put your finger on where the ripple is? Not really, because, there's just like, it's rippling out all around the water. There's no particular position. However, though, right, when you skip rocks, there are small ripples which, well, you can't put your finger on one exact point in the water where the ripple is. There's some small area that the ripple occupies. So between particles and waves, there's varying degrees of localization. Classical particle, like a cue ball on a pool table, is fully localized. You can put your finger exactly where it is. Waves, on the other hand, like the ripple, are not fully localized. They can have some localization, or like an ideal wave, if it's spanning all of space, then you cannot really put your finger at all. There's no particular region where this wave is or is not. The wave is everywhere. So we start off with this unlocalized wave, and we are going to keep constructing our model by adding a second wave. This one is also ideal, but has a slightly different frequency. So now we get them superimposed on each other. They're overlapping. So what we get is, now our model is a superposition of two waves. If you recall, when you add two waves of similar frequency, you get this beat pattern where you have some points of basically no amplitude, then they surround this kind of packets, these chunky packets of beats. Now, that means that our wave doesn't really occupy all of space evenly. There's areas where it has noticeable amplitude, there's areas where it doesn't. So now we're getting to a sense of localization. If we keep adding more waves to our model, eventually what we'll get is basically a flat line outside of a region close to the origin. So we'll just get like a single beat around the middle, centered at x equal to 0, but everywhere else, the resulting superposition would just be flat. So this resulting wave is called a wave packet, and because, if there's no amplitude anywhere, then the wave is really not there. It's only really where the amplitude is. Thus, the packet is said to be localized at the center. And now that we have a localized wave, or localized wave packet, then this is appropriate to be used to describe the position of a particle. Particles are, after all, localized. And believe it or not, but with this model, which is just a bunch of waves added together, not only can we get the position of a particle, but all the particles' properties can be derived from the superposition. So, summary: the quantum particle model is a particle described as a wave packet, a superposition of lot of waves. And the whole packet just resembles like a single beat. So this is, you can think of this kind of like as a true form of a particle. And what follows is that you might recall that every wave that composes the wave packet kind of has its own velocity, right? Time is frozen right now, but if we were to start stopwatch, waves are moving with some velocity. So when you add a bunch of waves together and get this, big beat, you actually have this sort of two components to the speed of the superposition. There's a phase speed, which is just the speed of one little wavelet here moving left or right, and then you have the group speed, which is the speed of the overall envelope of the whole beat moving left or right. So the whole package moving, that is defined by the group speed, while part within the package within the envelope moving is the phase speed. Here's a bunch of GIFs showing you the difference between them. Note that, for example, a standing wave is much like the one you see here, where the overall thing doesn't move. It's just the smaller components within the envelope that are moving up and down. Point being is that thus this wave packet has a measurable group speed to it that depends on the angular frequency and angular wave number of the packet. And that's all related to the, again, to the frequency and wavelength. And from this formula, actually, you can show that the group speed of a wave packet actually describes the speed of a particle. So, for example, any particle, classical physics has a kinetic energy related to the square of the momentum, and therefore, if there's no potential energy, then all the energy for the particle is just its kinetic energy. So the energy is then related to the square of the momentum. And then if you look at the group speed of the wave packet, you can rewrite it in terms of the energy and the momentum of the particle. So what this term is saying here, the d over the, this is a derivative. This is basically looking at the relationship between the angular frequency of a wave packet with respect to a change in the wave number, and that ends up being related to the change in the energy of a quantum particle over the change in momentum. And if you carry out the derivation between a particle's energy and its momentum, which is supposed to be the group speed, you'll get the particle speed. So the speed of the wave packet is the particle speed. Therefore, we can use a wave packet to describe a particle. And here's the derivation. So in this quick quiz, basically you have a sort of roadblock in the highway. So cars have to kind of swerve in a semicircle around it. And thus we're asking what the group speed. So the individual speed would be, the speed of any car moving around the blockage, but the group speed would be the overall shape of this sort of distortion in the lineup of cars because of the blockage in the way. So this blockage isn't moving, so the car's only curving around it at this particular point in the highway, which means that this like envelope that wraps around the blockage, that wraps around the whatever wreckage happened, doesn't move. So there's no group speed. There's just cars moving independently around the blockage. So there is some phase speed because cars are moving, but the packet itself is just based at the point on the highway where the accident happened. Anyways, that's all for now. I hope you join me next time. Thank you.